Okay, so welcome everyone. This is the fifth lecture. Today we're going to look at interest point detection and optical flow. So we have almost finished the conventional computer vision block just today and next week about similar stuff. But so far, let's just recapitulate what we have been doing. So we have looked at pixel level properties like color, for example, or edges, gradients, and how to extract these properties. And also we have looked at algorithms that give us object level properties. So whether there is an object or where does it move. And today we're going to look at all the stuff in between. So image structures that we will track through time, right? Today I'm going to first introduce you to the concept of key points and interest points, and then we will show you how to find these again in consecutive frames. This is an example of what can move and what the causes for image motion are. So first, obviously, there's object motion. So if an object moves, we will see something moving. But also if the camera moves, everything will look differently between frames, and a priori you don't know whether the object moved or the scene or the camera. You can use information about what moved to, for example, stabilize videos. You can use information about informative points, so these interest points, to not just find those again in consecutive frames, but if you have two recordings, maybe one showing a template image and a search image in which you want to find this object, you can use interest points also to find those objects again. This will be covered in the next lecture. Interest points can also be used to stitch different recordings together to a panoramic image, and you can use similarly those features to create a 3D reconstruction of the scene. So to summarize the problem setting for today, we have object or camera motion introducing changes in our images, but we usually don't know whether the object moved or the camera moved with respect to the scene. So what we instead do is we compute the image motion, and from that image motion we'll be able to infer whether an object moved or the scene. Okay? Now, optical flow comes with a problem that's called aperture problem, and it's basically saying that we have a 3D scene which is projected onto a 2D plane, and although we as humans we know the barber pole is like a three-dimensional object that has a rotary motion, so that every position on this thing rotates upwards from our perspective here, but the image flow is, or the image motion is leftwards from what we see here. Now, why is that called aperture problem? Well, if you consider this object here and it's moving from the previous position or the previous time point to the current time point about this vector here, but then you would just consider a small image region around maybe that position here, it appears that the image motion that the object moved almost in a perpendicular direction. Yeah? And this is due to us not knowing about the global motion, us not being able to consider global information about the object, and so forth. So we will start by approaching the optical flow problem with, again, the simplest algorithm possible for this. So we'll compute something that's called dense optical flow, which just means every pixel will be sought in the next frame. So consider this image here, and for those who don't know that picture, that's pretty, it's an historical computer vision photo. Probably not used as much these days, but for nostalgic reasons, I will show this here. So consider this image here and an origin point located at this blue dot, and we'll look just at this window, right? So our input region here looks like that. Now, the image, the object, or the camera moved, and so the next frame appears as a shifted variant of the original. Now, that same point now, relative to the image borders, shows something different, shows a different, piece of this hat. So what we'll do now, we will compare the original window that we had at the original position with different locations around the original position. So for example, that region here, yeah, it looks almost the same. It has some skin color here, and then this sharp edge of the hat here, but it's not the same. And so what we'll do is we'll shift our search window around our initial position, and then we'll hopefully match with that target position, that position that is the actual sought displacement of the original position. Okay, so how can we match two image patches? Well, one obviously is by comparing them on the pixel level, subtract each of these pixels, square those differences and sum these differences up, or the square differences up. And that's called SSD for sum of squared differences. So the equation is pretty simple. Let's think of I and J as two different images with the same size. So we can iterate over X and Y, all the pixel positions within I and J, and subtract respective pixel brightnesses, square these differences, and sum these up. Question: what would be the value for a perfect match? Okay, so remember we wanted to find the displacement of a small window within an image such that it optimizes this SSD. Optimizing means minimizing, so this looks like that. Let IT be an image at time point t, and IT plus 1 the consecutive frame. Now what we really want to do is we want to find delta x and delta y, that's the motion vector of that little window within I, and we'll iterate over all the x and y positions within that window, and we add this displacement for the consecutive frame, so which basically means we shift that window. We take those differences, square these, and sum these up, and we have our SSD. In contrast to minimizing the differences, we could also maximize a similarity score. For example, a correlation metric, which, for example, could be a dot product, right? So remember, I remember my fondness of the dot product. But you should always center our vectors in little excursus y that is. So imagine we have an n-dimensional space, and we have vectors in that space, and this is our center here. So we could compare these vectors by using the dot product. Think of the dot product as the projection onto one of those two directions. Remember, one of those guys needs to be normalized to length 1. And so if you have two vectors, one pointing there, one pointing there, the projection is negative, right? So these will be very dissimilar. Now, if your reference point is very far away from the point cloud, the rest of the world will appear very similar, right? So comparing these two vectors now from this reference here will appear very similar, right? Will give you positive dot product. Okay, so whatever metric you want to optimize, whether it's maximizing your similarity score or minimizing some kind of error function between your pixel patches, the general procedure to now match those blocks is this. So for each pixel position xy in our source window, a source image IT, remember we want to find an image motion for each of those x and y's. We iterate now over all possible or all allowed image motion vectors, delta x and delta y, and these need to be bound by a so-called search window. So given that one position, we have a window to find in which we will have a look whether something around that target or that source position can be found here or there or there. So we'll compute for example, your metric, maybe SSD, maybe something else, between your source image at location XY and your future image at location x plus delta x and y plus delta y, and we'll use respective match windows, W match. Yeah? So we're not just comparing image brightnesses at these positions. And then in the end of this, we need to store the flow vector delta x and delta y for each of those positions. Now, we'll complete the pseudocode for what kind of delta x and delta y's do we store these respective values. So your task in the current exercise is implement this block matching method on two different data sets. One is a moving camera on a car, another is a moving camera out of a car. So I'm hoping to see something cool here. Again, dense optical flow means we have a flow vector for each input pixel. But this may sometimes not work. Why? Right? So that's a question I want to ask you. What do you think would be reasons why we can't find a certain pixel or a pixel region, in a given frame consecutive to the one that we start with? So if finding a displacement vector for every pixel in the image doesn't work for some unknown reasons, we will only do that for pixels that will work, and that's called sparse optical flow. So we will identify only a subset of all the different pixels that exhibit certain properties that predict good reproducibility. So what does that mean? Well, it means we can find those things again in new frames. So these could be, for example, corner points or other image structures. These are called interest points or key points, and we will look at how to find them and how to define them in the next couple of slides. So, question: which of these points do you expect to be well, traceable, trackable? is it the one on the clean wall? Just, imagine the wall would move or the camera would move. Or is it a point on a blurry kind of edge of the pool? Or is it a point that has edges in pretty much all directions? Well done. I hope you would answer with, answer 2. Okay, so let's think of how to express that idea. Okay, let's start with a concept that's called self-similarity. It was introduced in a paper by Moravec, the so-called Moravec's corners. Now look at their self-similarity, right? So corners defined by their window, like the black one here, now will be chosen when they have low self-similarity. So what this is basically, we compute the sum of squared differences between the original window and the number of neighboring windows. So, right, so our I of x and y is compared with a shifted version of this in a match window W, and we'll, add up all those squared differences. Now we'll do that with for a number of x and y shifts, delta x and delta y, and then we'll sum up all those differences to have this index SS, or self-similarity. Now, what kind of corners, what kind of points, what kind of original windows do we like to identify? Well, exactly those that have low self-similarity, right? So, because if they move, we wouldn't be able to find them again because their environment, their neighborhood, just looks very similar. Yeah? So that's the whole concept here. So what we'll do is basically or implicitly do a block matching here, and we'll identify those corners, those points in the window that stand out of their neighborhood. The problem is that we'll actually have to do this this block matching explicitly, right? So we'll have this window and we'll take this window and then we match both, and then we'll do another time with another window and so on. And this just is very slow, and that's why people just don't do it anymore. But this idea can be used to introduce you to another algorithm, which is called the Harris corner detector. Which is a little bad because the paper was by Harris and Stevens, but nobody just calls them Harris and Stevens' corners. Yeah. So the core idea of this paper can be summarized in maybe 5 or so steps, and that's what we'll do. We'll start with the definition of the sum of squared difference for one, shift, one window, one of those green windows. Located at delta x and delta y. So that's the equation that we already know. And the trick here in this paper is that we'll approximate this image at the shifted location. So, the Taylor approximation just states that any function at the shifted location can be approximated by the image derivative at the original location times how much we shifted, right? So we kind of expect the function to be linearly, approximatable. Is that a word? And anyway, so this part here becomes this approximation. For those who don't know why that works and why we can do that, just ask that in the Q&A session. Right? Now, we'll plug this in to this, and then you see this I of x and y, and again, minus I of x and y, so that these two parts, become 0, so what will remain is just this, dot product between the gradient and the shifted vector delta x and delta y squared. Yeah. So why does that make sense? Well, you know, the sum of squared differences in the direction of the gradient is, you know, expected to be high, right? Because that's exactly the shift in which we expect, you know, those two windows to be different. If we have an edge that is oriented like that, our gradient looks in this direction. And if we take a window shifted in this direction, so this one here, then the dot product is 0. So we expect our sum of squared differences to be very small. Yeah. So intuitively, even that approximation makes sense. Now, let's continue this. We can just resolve the square, right? So this would be, you know, that part squared plus 2 times this plus this squared. I just, you know, put it here. And then we can, like, you know, pull out those shift vectors. And it becomes like a vector matrix times vector product, which has a very nice property. Now, so, you know, to summarize, what we just did is that the sum of squared differences of the image with a window that is shifted by delta x and delta y is that shift times a matrix that, you know, looks like that, times again that shift vector. Now, A is called the structure tensor, and now the point of the paper is that A contains all the information that we need to identify corner points or disregard, you know, non-corner points. And that is because in the sum of squared differences, the delta x and delta y's, so all these window positions, they are the same, right? The only thing that changes is the position of the black window. And all the gradient information contained here, those contain the information about whether the black window is a corner point or not. Yeah? So, but how do we extract from this 2 by 2 matrix A information about whether it is a corner point or not? And to understand that, we have to look at 3 example cases. One with a window that has practically nothing in there. There's a little noise, so the gradient in, you know, x and y direction is distributed, you know, in a tight focus around 0. But for patterns like this edge here, where we do have an x gradient, right? So vertical edges means a lot of x gradients. We see that this increases the variance of this distribution. But for those patches that have corners, right? So those are the ones that can be tracked well in all different directions. This distribution is even larger. Now, how can we extract exactly this property? So information about how much spread you know, this matrix represents. And for those of you who know the covariance matrix in principal component analysis, this is a simple answer. We'll use the eigenvalues. For those of you who don't know, just hit me up in the Q&A session and I'll explain briefly. So since we do not have an explicit you know, distribution, we only have those 4 numbers in A, obtaining the eigenvalues gives us information about this spread. So for a 2 by 2 matrix, we'll get 2 eigenvalues, and we call these lambda 1 and lambda 2, and we'll define in area, you know, where both eigenvalues are large to be that area, or to correspond to those patches that we're interested in. Edges, whether they are here or there, will have small eigenvalues. Yeah, one of those will be small, and very, very small eigenvalues for both eigenvalues probably means there's nothing in there, so we'll disregard these windows as well. So the authors propose also a list of simplifications or improvements to the method. So one is that we'll use a Gaussian window. Remember our structure tensor is the sum of the squared x gradients and the squared y gradients and the product of the x and y gradients. And the sum is over all x and y positions in the window. What we'll do is we'll use a Gaussian weighting of such that the center gradient information are more important than the peripheral gradients. And since the eigenvalues are expensive to compute for all the different image locations, Harris and Stevens propose using like a helper value that's called R, and this score here is a function of the matrices determinant and the trace. And so for those of you who don't know what a determinant is, that's just for 2x2 matrices, the product of A and D minus B and C, and also the trace is just a sum of diagonal components. Good. Now we have an R score, and we'll just threshold it to binarize windows, right? So image locations to either be above a certain threshold for R, those are the corners that we want, and below this threshold are the ones that we disregard. Robert Collins, an instructor at Penn State University, has nicely summarized the algorithm here. I'm not gonna write this down for you. I just copied one of his slides that you can find here. I hope he's okay with that. By the way, that's the way we compute the sum of the gradients. We just use the convolution with a Gaussian kernel, and the rest is something that you can find in the slides. So your task for this exercise here is to implement exactly that procedure and to find and display Harris corner points. Okay, so that was Harris's corner point detection. We'll conclude the whole lecture with the second part, which I'll upload very soon.